Coulombs law. Now we're going to actually calculate the electric force between charged particles. So Coulomb's law is very similar to Newton's universal law of gravitation. They're both inverse squared laws. They're both essentially calculations based on fundamental forces. So it's not surprising that they're similar. In any case, Charles Coulomb lived from 1736 to 1806. So he was almost a contemporary with Benjamin Franklin. But again, he studied the electromagnetic force, or the electric force, and magnetism, and also did some work on material strengths. So in 1785, he published he basically published his discovery about the forces between charged objects. And again, the form of his equation was very similar to Newton's universal law of gravitation when we look at it. There's, first of all, a constant out front. It depends on the product of the properties of the objects that are interacting. For Newton's universal law of gravity, it was, of course, the masses of the objects that would be important or proportional to the forces. Here's the product of the charges. And of course, there was the inverse square relationship between the force and the distance. So again, a lot of similarities there between the gravitational force and the electric force. Now, to do this, he actually came up with a brilliant experiment. He used a torsional balance. He basically suspended a wire on a balance with charged spheres, similar to I believe it was Cavendish's experiment to find the universal gravity constant. And he measured the amount of deflection created by the electrostatic force and was able to develop this relationship again between the distance and the force, obviously. And here's another view of sort of how that would be set up. You have Q1, which would be a charge introduced through this rod right here. You had Q2, the charge on this dumbbell right here, which was then suspended by this fiber. And again, you could basically take the torsional force on the twisting wire and convert that into a force on some sort of scale. So basically what you're doing is you're turning the wire, the fiber, into sort of a helical spring, even though it's not a helix. So it's somewhat similar to what we see on a torsional spring on a weight scale. Okay, let's look at Coulomb's law in vector form. For this course, we try to keep it simple in a scalar form. And in its vector form, it's a little harder to see exactly what's going on. So we can either write it like this, where the force on 2 due to 1 is equal to k q1 q2 over the position vector. That's what this is right here. This is the position vector, or the vector pointing from one charge to the other charge. Okay, you can write it like that. Or alternatively, if we want to write it with unit vectors, we can write it this way, right here. So really what we have is we have the scalar calculation that you do normally, the electrostatic constant times the product of the two masses divided by the distance between the two masses squared. And then the unit vector would point in the direction of the force. So, it'd basically be pointing either from 1 to 2 or from 2 to 1, depending on if it was an attractive force or it was a a repulsive force. Actually, I should say it would point toward the charges or it point anti-parallel from that direction. Again, depending on if this were an attractive force or if this were a repulsive force. Sometimes you'll see Coulomb's law written just a little bit differently. This is where the electrostatic constant is equal to 1 over 4 pi epsilon 0. Epsilon 0 is what is known as a permittivity of free space. And this constant is commonly used in Gauss's law, which we'll be talking about in the next chapter. But again, there's the vector form. And the vector form, of course, gives you both magnitude and direction. The approach that we have with a lot of these problems is you can calculate the scalar value of the force first, and then using a diagram, determine what the direction is. Okay. So main points of Coulomb's law, obviously it's a 1 over r squared law. It's a 1 over the distance squared law. It depends on the product of the magnitude of the charges, okay? But it also depends on whether we're dealing with opposite charges or like charges. Opposite charges attract. So whenever we have a positive charge, it is attracted to a negative charge. Like charges repel. Positive repels positive, negative repels negative. And that's why most objects, in fact, are neutral. Most objects are electrically neutral because the Coulomb force would be very, very large if there's an excess of positive charges, an excess of negative charges with any other object, that it would basically try to neutralize itself by tearing charges from other objects. So throughout the universe, we don't see many things on the macroscopic scale which have a large electrical charge. On the microscopic scale, obviously the proton and the electron have relatively large charges for their size because they are really the source of charge. So again, the force between charges is directly proportional to the magnitude of each charge. If we double the charge of one charge, we double the total force. If we double both charges, obviously 2 times 2 gives us 4 times the force. Again, inverse square law, whenever we double the distance, the force drops off by 1 over the distance squared. If I make the distance twice as large, the force drops to 1/4. Okay. Now, obviously, if I increase the distance by a factor of 3, the force would drop to 1/9. Okay. Let's do a little calculation here. Here we're going to ignore the vector nature of the force because it's not really all that important. But we are going to ignore quantum mechanics. We're going to sort of go back in time, and we're going to look at sort of a Rutherford model of an atom. We're going to look at the Rutherford model of the hydrogen atom. And of course, we have the proton at the center with our positive charge, and we have the electron orbiting it with its negative charge. Okay. Now, according to some measurements, the Bohr radius, the classical radius, which the electron orbits the proton, is 5.3 times 10 to the minus 11 meters. Now, if we look at the quantum mechanical view, the electron is actually occupying a region around the proton in sort of this cloud. You know, it has this probability of being in different locations. So this radius, I believe, would represent the average distance that this probability cloud would have if you average it over the probability, if that makes any sense. Okay, so we have our classical distance. Of course, we know the mass of the proton, the mass of the electron, and we have the charge on each. I've left off the negative from the electron because, again, the positive versus negative, that only really matters when we're worried about direction. We're not worried about direction here. We understand the electron is going to be pulled inward toward the nucleus. Okay, so let's do something here. Let's compare our electrical force, the electrical force according to Coulomb's law, to the gravitational force. And we're going to show that it's clearly not the gravitational force that holds the atom together. Okay? You can calculate that. We know that the planets are held in orbit around the sun through the gravitational force. And Rutherford saw the atom as sort of being similar in planetary structure. But we're going to clearly show here that the electrical force far exceeds the gravitational force by a huge amount. We're talking, tens of magnitudes difference between the two. So first of all, we use Coulomb's law to calculate the electrical force between the two. Notice I have my electrostatic constant out front. I take the product of each charge. Again, not worrying about the sign. And here's where a lot of mistakes are made in calculations. It's 1 over the distance squared. Square the distance first before you do any other mathematical operations. Remember your order of operations. That powers, in this case, the power of 2, is calculated first, and then you do your multiplication and division afterward. So if I do that calculation, I find out that the force is very, very small, as I expect. It's 8.2 times 10 to the minus 8 newtons. Okay, if you want to use other units, that would be 82 piconewtons. Very, very small number. Okay, now I'm going to do the same calculation, but this time I'm going to do it for gravity. So there's our old universal law of gravitation equation, which we came up with Newton. Newton came up with this. Now notice that I'm using a much smaller constant out front. The electrostatic constant is 8.99 times 10 to the 9 newtons per coulomb squared, and then times meters squared, right? This one is newtons per kilogram squared times meters squared, okay? But it's 10 to the minus 11. So right off the bat, I'm going to get a small number here. Also, the mass is in kilograms. These are smaller numbers than the Coulomb in charge that I had, but I still have the same radius. So I square the radius and then I multiply this. And although my previous force was small, this force is ridiculously small. 3.6 times 10 to the minus 47 newtons. Okay, I can't really think of too many numbers in physics that get that incredibly small. So our force due to gravity is very, very small. And if I take the electric force, okay, take the electric force between the electron and proton, and I divide it by the gravitational force, I see that I'm off by 39 magnitudes, okay? 39 magnitudes difference. That's not 39 times different. That's a 2.3, okay, with 38 more zeros coming after it. Huge number. I won't even write that out. 39 times magnitude greater. And what that shows us is the electric force is a much stronger force than the gravitational force. But why is the gravitational force so dominant on a large scale, whereas the electric force is only dominant on a microscopic scale? Well, first of all, I gave you a little hint to the answer earlier. I said, the forces, the electric forces can get very large by having an excess of electrons or a deficit of electrons, where once you get a charged object, it'll just rip electrons off from its neighboring bodies to try to neutralize it out. So microscopically, we can get appreciable charges, but on a macroscopic scale, objects are always trying to discharge themselves. Clouds build up charges. We talked about lightning earlier. Well, they're always discharging themselves in the form of lightning bolts, trying to get rid of that excess charge due to that force. The other thing we have to remember is that this force is actually attractive and repulsive, okay? So it can be attractive and repulsive. And the attractive and repulsive nature sort of has it on a macroscopic scale, zeroing itself out, okay? All the negative charges and the positive charges in one object are going to sort of cancel each other out if it's electrically neutral. And as we said, most objects strive to become electrically neutral. The gravitational force, however, is cumulative, even though on the atomic scale, it's so insignificant, okay? And it's even insignificant when you get to like Avogadro's number of molecules, okay? 10 to the 23 is still, tens of magnitudes less than 10 to the minus 47. When you start getting onto a planetary scale, then the forces become appreciable, okay? We know this because 1 kilogram sitting on the surface of the Earth is going to experience a force of 9.8 newtons. So our electric force being repulsive and attractive, okay, has a tendency to pretty much neutralize itself out on a larger scale, okay? But the gravitational force is always attractive, so it just gets bigger and bigger and bigger as we add more and more mass, okay? But again, our electric force does have, if you want to say per matter per kilogram, even though it doesn't act on mass, and kilograms a measure of mass, particle for particle, the electric force tends to be a much stronger force, okay? And later on, we're going to talk about electric potential, and we'll find out that if you take the gradient of the electric potential, that will give you the electric force directions. But we can imagine a particle with mass being attracted to another mass, all right, where the gravitational field lines would point in the direction that it would experience that force. And the same thing is true with the electric force, that positive charges are pulled in the direction of a negative charge. Okay. So same sort of way we can envision things. And again, we have to think about the vector nature of the electric forces and decide, whenever we're solving one of these problems, what direction the vector is going to go. So in this case, I have 2 positive charges. So r is going to be the distance between them, okay? And the vector is going to point away from the other like charge. They're both positive. So this force points this way, this force points this way. And I always have trouble with this because I do make the mistake of saying, this is the force due to 2 on 1. So we'll write that as F21, okay? F21 is actually the force on 1 due to 2. Likewise, look at this up here. F12 is a force on 2 due to 1. I always think it should be written the other way. Write it the way that would be more natural to say the force on 1 due to 2 should be F12. It is the force due to 2 on 1. So that always sort of got me, that nomenclature that they use there. Obviously, if they're opposite charges, they're going to pull toward one another. Here we have a positive and negative charge. You can see the vectors are pointing toward one another. So in setting up an electric force problem, you always want to make sure that you draw it out so you know exactly what's going on, because we can calculate using Coulomb's law the magnitude of the force, but the direction of the force, it's really much better to see where it's going drawing a diagram. Okay, let's do an example here. We're going to do another calculation. This is going to be a little more challenging, though. In the previous calculation, we just said, oh, what's the force? I know the distance. I know the charges. What's the force? In this one, we're going to do a little bit of a balance, okay? And just see how we're still sort of ignoring the vector nature in some respects, but we have a negative charge. It's going to be pulled to the right by a positive charge and pulled to the left by another positive charge. So there's a little bit of direction that we have to worry about here. Okay, in any case, let's get into the problem. 3 charges lie along the x-axis as shown in the figure. Okay, so our x-axis is, going off in that direction. The positive charge Q1 has a charge of 1.5 times 10 to the minus 5 coulombs. When we do a lot of these problems, you'll find out that the charge is going to be really a small number of coulombs, like it'll be in millicoulombs or microcoulombs, because 1 coulomb of charge is a massive amount of charge. It's located at x equals 2 meters. And the positive charge Q2 has 6 times 10 to the negative 6 coulombs, that's 6 microcoulombs. At the origin, x equals 0. Okay, so just to get everything straight right here, if I were to draw an x and y axis, here would be my y axis. So the origin is at the location of 2, and there would be my x axis. Okay, so the question is, where must a negative charge Q3 be placed on the x axis such that the resultant electric force is 0? Okay, now here's an important point. Q3 can be anything. Q3 can be any size charge because it's going to be proportionally pulled the same by, it's going to be proportionally pulled for its distance and the charge of Q1 as Q2 pulls. Okay, so I want to find out that distance. So the way I set this up is I say, okay, what do I know? I know the 2 positive charges are separated by 2 meters, okay? But we're not really worried about them moving. They're just going to be stationary. So I'm going to create an unknown value, x, which is going to be the distance between Q2 and the negative charge Q3, okay? And then I'm going to say there's another distance, which would be the difference between 2 meters, okay, minus x, which would be the remainder distance, okay? So for instance, if this were 1 meter, then the distance between Q3 and Q1 would be 1 meter. It's just the difference between the two. Okay, we know that's not going to be the case because if you look at the charges, Q1 is larger than Q2. So my expectation is that Q3 is going to have to be closer to Q2 to balance the force. Hope I said that right. Okay, so the first thing that we're going to do is we are going to calculate the magnitudes of the forces. We're going to look at, I noticed a little problem right here. Okay, we're going to look at, no, this is fine, the force on 3 due to 1. It's going to be K Q1 Q3 over R 1/3 squared. And then we're going to also look at the force on 3 due to 2. Okay, so these two forces have to balance out one another. These two magnitudes have to be equal to one another because the forces have to be equal and opposite, because this force has to pull as hard as this force pulls here. Equal and opposite forces. So I set it up in the equation where I calculate F13, I calculate F23. I'm going to say both of these add up to be equal to 0. Okay. Remember, F23 is pointing in the negative direction. F13 is pointing in the positive direction. That's why I have a negative value there. Set them equal to 0. Okay. And notice when I'm putting this through, I have a few unknowns. I don't know Q3. Okay, that's fine, because we're going to see that disappear. I also don't have distances here. So I got to substitute 2 minus x and x in the denominators before we square them. Okay, so now I'm just focusing on substituting in this equation right here, substituting those two amounts. And notice that I can pull this common constant out front and this constant out front. Okay? Actually, if I pull Q3 out front, it's not letting me draw. If I pull Q3 out front, we're going to find that Q3 and the electrostatic constant cancel out. Okay? How do I do that? How do I cancel them out? Well, I've got 0 on the right-hand side. I can divide both sides by Q3. So Q3 cancels out with Q3. I can divide both sides by the electrostatic constant. Okay? Doesn't change 0, because 0 divided by any number is still 0. Well, 0 divided by 0 is actually 1, but that's a whole other mess to talk about. So I'm left with this relationship right here. Okay? I'm left with this relationship right here, which I recognize I can turn into a quadratic. Okay? How do I know that I can turn it into a quadratic? Well, notice if I multiply this out, I get x squared minus 4 meters squared x plus 2. I'm sorry, plus 4, because 2 times 2 is 4. And this is also x squared. And I can multiply both by a common denominator and basically put that quadratic on top. Okay, what do I mean by that? Here is my equation. I take that and I just expand it out to all the different terms. I get to this point right here. I'm going to take this and put it on the other side. And I can cross multiply. I can multiply both sides by x squared and multiply both sides by this term here. And when I do that, I get this equation. Now I'm going to group all like terms. I'm going to put all the x squareds together. Okay, so here are my 2 x squared terms together. Here are my x terms. Here are my non-x terms. Okay. I come up with this. I recognize that it's divisible by 3. And here is my quadratic. I can find the roots to that. I can find out the x's that give me a location that is balanced. Okay, so the rest is algebra. You remember how to find the roots to the equation, right? You can use negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, and that's what I do. There's that little quadratic formula. And I plug this in, and interestingly, I find out that the roots are the following. Okay, 1 is going to be a physically, physically a root that makes sense. At 0.8 meters, that makes sense because that's less than 2 meters, but more than the origin. Okay. Now, this one right here, this is sort of a curious result because that would put the charge on this side. Okay, that would put the charge on this side, but it wouldn't be balanced because it would be attracted to both charges. So this solution right here doesn't work. The 0.8 meters makes sense. Okay, so here we saw 2 things. We sort of did a one-dimensional calculation because we only considered the x direction. The symmetry meant that we didn't have to worry about any y components. But we saw, as we know, that forces add up. And in this case, it was an equilibrium. So we just take the sum of the forces and set it equal to 0. We plug everything we know into the equations. X was an unknown, and then we could find x based on the quadratic formula. Okay, here is a two-dimensional problem. And we're not going to do three-dimensional problems because the two and three-dimensional problems are very, very similar. You have similar techniques. The three-dimensional problem is just, well, it's more of a hassle. It's more of a hassle to do. Okay, so why don't we do this one? We're going to look at a positive charge, a negative charge, and another positive charge, and we want to find out the total force on the third charge, which is a positive charge. Okay, first thing you always want to do is draw a diagram. In this case, we put the location of each of the charges. Q1 is at the origin, as indicated here. So again, drawing my X and Y axes, right? There's my X axis, my Y axis. I have Q1 at the origin. Q2 is 3 meters above Q1 on the Y axis. And sure enough, that's where I put it. But Q3 is 3 meters above, okay? So 3 meters up and 4 meters to the right, 4 meters in the positive X direction. So it's located right there. So I'm fortunate in that the way that I've set this problem up, the geometry is actually a 3, 4, 5 triangle. You probably would have noticed that, right? Because a line from Q1 to Q2 is along the y-axis. A line from Q2 to Q3 is in the X direction. X and Y are perpendicular. So from Q1 to Q3, it is the hypotenuse of this 3, 4, 5 triangle. Two of the sides are 3 and 4 respectively. So the hypotenuse, as I said, is 5 meters. Why is that important? Because we need to know the distances between the charge in order to find out the magnitude of the force, okay? So the force on 3 due to 2 is just going to be in the X direction. That's fine, okay? But the force on 3 due to 1 is going to be sort of at an angle. So let's draw those out. Let's get rid of our triangle for a second. And again, we're going to draw out these forces, okay? F2, 3. There it is pointing in this direction right there. Why is it pointing in the negative X direction? Well, we know it points in the negative X direction because we have a negative charge and a positive charge. The force is attractive. So we imagine Q3 being pulled toward the negative charge, okay? Now we look at the force on 3 due to 1. It's a repulsive force. So the force is going to be off in this direction, pointing away from Q1. It's going to be pointing off at an angle. Okay? So I've sort of set up exactly how I'm going to solve this whole thing. I'm going to find the electric force on Q3 due to the other charges. And because it doesn't say magnitude of force, I want the magnitude and the direction. Now, this is similar to some of the problems that we did in Physics 1, okay? Where we want to add up the different forces. We want to find out the total force in the X direction. That's going to be equal to F13X plus F23X. We want to find the total force in the Y direction, which in this case is only one component. That is going to be F13Y, because F23Y is 0. There's no Y component. Okay? So very similar to what we did when we did mechanics. Okay? We find the magnitude of a force. We resolve it into its X and Y components. We had X to X, Y to Y. Then we put it back together and find the magnitude of the total force. Okay, and we can use inverse tangent to find the angle if we want the angle of the direction. Okay, so I always like to start by just calculating, first of all, our values, okay? What are our scalar values? Okay, what's this equation right here? F23 is going to be equal to, just use Coulomb's equation, 5.62 times 10 to the minus 9 newtons. But as we said before, notice it's pointing in the negative x direction. So not only do I have F23, I have F23x just by putting a negative sign in front of it. Because, of course, there's no y component. All right, so what did I do? I found the magnitude of the force, and then I resolved it into its x and y component. There's only an x component, so I don't have to do anything further, and I'm fine. Okay? That's going to be a little more complicated as we do F13. Now, when I go off to do F13, I recognize it's a 3, 4, 5 triangle. If I didn't, I would have to do the Pythagorean theorem, right? Square root of 3 squared plus 4 squared is 9 plus 16. 9 plus 16 is 25. You take the square root of 25, and we get 5. 3, 4, 5, 9. Okay. So I know the distance, and if you're not convinced of that, you could have found the distance. I know the distance. I plug that into my equation right here, and what I get is the magnitude of F13. But remember, some of it's in the x direction, some of it's in the y direction. Okay, so I can do this a number of different ways, all right, in terms of finding what is each component, because there's an angle here, theta. Okay, we know that the x component is the magnitude times cosine theta. We know cosine theta is adjacent divided by hypotenuse. So 4 divided by 3. Oh, that's easy, right? That's really easy. That's just 0.8. Okay. And sine for the y direction, I do the same thing. Except for I'd use opposite over hypotenuse, which would be 3 divided by 5, or 0.6. Okay. So I could do that. I could know that the angle here, I don't know the angle first, 3, 4, 5 triangle, what is it? 30, it's like around 37 degrees, 37 degrees. And find the cosine of 37 point something degrees and the sine of 37 point something degrees. Okay. However you do it, you need to resolve that. Okay. And in fact, yeah, if you don't know that angle, you can actually calculate it by using inverse tangent. You know, the x component divided by the y component divided by tan gives me 37 degrees. Okay, so I find my x component, I find my y component. Here's my x component of that, my y component of that. Okay, and now I'm going to add the x's to the x's, get my total x. And since there's only one y component, it simply becomes F13y. Okay, so again, F13x, which I just found, plus my previous result, F23x. Okay, we add them together. Here's our current value. Here's our previous value. We add them together. We get this for a force. Okay. It's my fx, that's my fy. Once I have my x and my y, I can take the sum of the squares and then take the square root. And that's going to give me my total force. So the total force that Q1 experiences is 7.16 times 10 to the minus 9 newtons. Okay. It is pulled with 6.5 times 10 to the minus 9 newtons in the y direction and 3.01 times 10 to the minus 9 newtons in the x direction. The angle of the vector Fy over Fx. Yeah, before we had 37 degrees, but that was only one force. Now when we combine the two forces, the total Fy force divided by the total Fx force, arctan, tells me that the total force is going to point at 65.2 degrees. Okay, so this is a really good problem to practice. This is a good problem to look at because it requires you to figure out distances. You need that for calculating the magnitude of forces, and forces you to resolve vectors. It forces you to, put them together at the end and use arctan to find the direction. Okay. Again, you got to think a little bit back to physics 1 when we're dealing with multiple forces. Basically, when we take the net force, we're adding all the forces and putting them together. So the superposition principle says the resultant force in any one charge equals the vector sum of all the forces. So if you have 2 charges pushing on one charge, you got to add both forces up like we did before. If you have 10 charges pushing on one charge, you got to add up 10 different components. Okay. All right.